Hello students, my name is G. Nikita, M. Pharmacy, Assistant Professor, Department of the Pharmaceutical Chemistry. So I will deal the pharmaceutical inorganic chemistry from the first years. So today we are going to discuss about the theory of indicators. So today's topic name is theory of indicators. So in this we will discuss the introduction, means what is the indicators and what are its importance and why we have to use the indicators, and theory of the indicators means in what are the theory of the indicators. Means in this we will discuss about the introduction, means what is the meaning of the indicator and why we are using the indicators, and also the theory of indicators, means what are the theory of indicators have been involved. So introduction, let's see what is the indicator. So the indicator is the chemical substance which is used to determine the end point. Means mainly these indicators are used in the titration process. So in the titration process, we will use the indicator in order to know the end point. Means when we perform the titration, like we will take the known concentration in the burette, that is titrant, and the titrate should be taken in the conical flask. So the titrate is unknown concentration. So known concentration should be taken in the burette. Unknown concentration should be taken in the conical flask. So while performing the titration, we have to add the indicator to know the end point. So how we can able to know the end point? By adding the indicator, means we can able to observe the color change. So before adding of the indicator, there will be one color, and after adding of the indicator there will be the another color. So by seeing or by observing the changing of the color, we can able to know that we got the end point. And also this indicator should, suitable indicators should be added for the solution. So if we add the suitable indicator for the certain solution only, we will get the color change. So if we won't add the suitable indicator, or if we added whatever the indicators what we want, means we won't get the color change. So in the acid base titration, organic substances like weak acid or the weak bases are the generally used as the indicators. So if you see in the acid base titrations, the weak acid or the weak bases, here we will use the weak acid or the weak base as the indicators. So they change their color within the pH range. So if you see the several indicators that we are going to use for the acid base titration. So I have already explained this table in the previous topic, like acid base titrations. So in acid base titration topic, I have explained these indicators that what we are going to use. See, I will explain it again. So indicators are phenolphthalein, litmus, methyl red, and methyl orange. What are their? Phenolphthalein, litmus, methyl red, and methyl orange. So its pH range of the phenolphthalein is 8.3 to 10.5. And it gives in acid is colorless. So when, as the phenolphthalein is the weak acid, so when we mix it in the acid, so acid and acid, so it does not undergo the neutralization reaction, so it remains same. So it gives colorless, so the color does not change. When we dissolve this phenolphthalein in the base, means it will give red or pink color. Next, litmus, its pH range is 5.5 to 7.4. So when we dissolve in the acid is red color, and color in the base is red. Next, methyl red, pH range is 4.5 to 6.5. So we will get the color in acid is red and color in base is yellow. Next, methyl orange. pH range is 3.2 to 4.5. Color in acid is pink and color in base is yellow. So see here, phenolphthalein pH range is 8.3 to 10.5. Color in acid is colorless, color in base is red. Next, litmus pH range is 5.5 to 7.4. Color in acid is red and color in base is red. Next, methyl red pH range is 4.5 to 6.5. Color in acid is red, color in base is yellow. Next, methyl orange pH range is 3.2 to 4.5. Color in acid is pink, color in base is yellow. Let's see the theory of the acid-base indicators. So there are two theories. See here, 1, 2. First one is Ostwald theory. Next one is quininoid theory. Ostwald theory, quininoid theory. So these are the two theories which have been involved in the acid-base indicators. So first one is the Ostwald theory. Next one is the quininoid theory. So let's see what is the Ostwald theory. So this Ostwald theory is mainly based upon the color change. So in this, what will happen means how we can able to find out the endpoint means based upon, it is mainly dependent upon the color change. So the color change is due to the ionization of the acid base indicators. So the unionized form as different color and the ionized form as the different color. So here in this, what will happen means this theory has been introduced by the scientist named Oswald. So this theory is mainly depend upon the color change. So based upon the color change, this theory is dependent. So the color change is due to the ionization of the acid base indicator. So the unionized form, before formation of the ionized form, it has the one color, and after the converting to the ionized form, it has the another color. So the ionization of the indicator is largely affected in the acids and bases, as it is either a weak acid or the weak base. So this indicators, it plays an important role. So in not only in the acid base titrations, in any type of the titrations, indicators plays an important role for the titrations. But if we see here in the acid base titration, because here we are discussing mainly about acid base titration, so here we have to use the weak acid or the weak base as the indicators. So in case the indicator is a weak acid, its ionization is very low in the acid. Means if we are taking the weak acid as an indicator, if we dissolve the weak acid as an indicator in the acid, means acid both are same. And here common ion effect will be formed. So that there won't be any color change. Means if acid and acid, it will be mixed, means both will become same and there won't be any neutralization process. So the color does not change. But when the acid and the base has been mixed, means it undergoes the neutralization process. So we can get the color change. Even if we see when the weak base is taken as the indicator. So if the weak base is taken as indicator and dissolved in the acid, means it undergoes the neutralization process. So the color will be changed. But when we mix this weak base as an indicator in the base solution, means due to the common ionic effect, there won't be any color change. See, I will explain it again. So Oswald theory means it is mainly dependent upon the color change. So the unionized form as one color and ionized form as the another color. So this indicator plays an important role in the titration process. So it may be either weak acid or the weak base we can take as the indicator. So for example, if we take the weak acid as an indicator when we dissolve in the acid, so acid and acid both are same. So it does not undergo the neutralization effect. So it forms the common ion effect. So what will happen? There won't be any color change. So when we mix the acid in the base means the solution will undergo the neutralization process and the color will be changes. And if we take the weak base as an indicator, when we mix the weak base indicator in the acid solution means the color will change because it undergoes the neutralization process. But when this weak base indicator dissolved in the alkali means base solution means there won't be any color change, the solution will be remains as it is because of the common ion effect. So if you see here, if we take the, for example, if we take the phenolphthalein and methyl orange as the indicators as example, phenolphthalein is the weak acid, methyl orange is the weak base. Phenolphthalein, methyl orange. See here, phenolphthalein is the weak acid and methyl orange is the weak base. So weak acid indicator and weak base indicator. First one, if we take the phenolphthalein as the example as the weak acid. So phenolphthalein means the hydrogen ions and pH has been separated. So when this phenolphthalein has been dissolved in the hydrochloric acid, HCl. See here, HCl. So H and Cl is separated. Hydrogen ions and chlorine ions will get separated. If we see here phenolphthalein, has and the hydrochloric acid, the hydrogen ions are common. See here H plus and H plus are common. So here the common ion effect is formed and also it is a reversible reaction. So here both are acid. See here phenolphthalein is also acid and the hydrochloric acid is also the acid. So when two acids have been mixed means there won't be any neutralization reaction, so there won't be any color change. So basically this phenolphthalein is the colorless solution. So when we mix this phenolphthalein in the hydrochloric acid means there won't be any color change. The solution will be remain as it is because there is no neutralization reaction and also common ion effect is formed. See here in the phenolphthalein hydrogen ion and in the hydrochloric acid hydrogen ion. So both are same. So there is won't be any color change. If you see here, this is the phenolphthalein. The hydrogen ion has been formed, and if we take the strong base, that is sodium hydroxide, the sodium and hydroxide ion is separated. See here OH and H are different. Hydrogen and hydroxide are different. So this hydrogen and hydroxide combine to form the water molecule. So it undergoes the neutralization process and we will get the end point as the pink color. Means this phenolphthalein when we add in the acid solution. So when the so basically phenolphthalein is the weak acidic in nature. So when this phenolphthalein is dissolved in the acidic solution means due to the presence of common ion H plus and H plus. So the common ion effect will be formed. So there won't be any color change. But when we dissolve this phenolphthalein in the strong basic solution, that is sodium hydroxide here, the hydrogen and OH will get separated in the form of water molecule, and here it will become the neutralization. So the color changes from colorless to pink. Next example is methyl orange. So if we took the methyl orange as the indicator, so methyl orange is the base. So methyl orange, when it is dissolved in the strong acid, that is hydrochloric acid, here the hydrogen and here OH will get separated in the form of water molecule. So the neutralization reaction will be occur. So the yellow color will be changes to pink color when methyl orange is dissolved in the hydrochloric acid. But in case of the base, when methyl orange is dissolved in the strong base, so here OH, OH are common. So common ion effect is formed. There won't be any color change. See here, if we take the phenolphthalein, it is the weak acid. So when the weak phenolphthalein is dissolved in the hydrochloric acid, so both are the acids. And here the common ion, hydrogen and hydrogen is all the common ion. So the common ion effect is formed. So there won't be any color change because it does not undergoes the neutralization process. Because both of them are acid, both of them are same. But in case of the base, when the phenolphthalein is dissolved in the base, that is sodium hydroxide, here H plus and OH is separated in the form of water and it undergoes the neutralization process. So the end point is pink color. So here we are taking both acids, but here we are dissolving the acid in the base. Next, methyl orange. So here what will happen when the methyl orange is dissolved in the acid? So here base is dissolving in the acid. So here OH and H plus OH and H plus will get separated in the form of the water molecule, undergoes the neutralization reaction. So the color will changes from yellow to pink. In case of when the methyl orange is dissolved in the base, means both of them are basic in nature. So this will form the common ion effect. So there won't be any color change in the end point. So this is about the Ostwald theory. So this Ostwald theory is mainly based upon the color change of the solution. Next, Quinault theory. So according to the Quinault theory, an acid-base indicators exist in two forms. So in two different structures, in structural forms, this acid-base indicator has been formed. So according to the Quinault theory, the acid-base indicators has been exist in two different structures. So first one is benzenoid form. Next one is quininoid form. See here, first form is benzenoid form and second one is quininoid form. So these two structural forms have the different colors. So if, for example, if we took one structure, if we take one structure, it is in the benzenoid form. So when it is converted to the quininoid form, its color will be changed. So two forms have the different color. See here, two forms have different colors. So the color change is due to the interconvention of one tautomeric form into another form. Means if you take the structure, in the structure, completely the structure won't change. Only there will be the slight change and remaining will be same. So that is the tautomeric form into another. Only one form mainly exists in acidic medium. So there are two forms I said, no, that benzenoid form and quininoid form. So among these two structures, one structure is mainly formed in acidic medium and another structure is mainly formed in alkaline medium. Alkaline means basic medium. So during the titration, the medium changes from acidic to alkaline or maybe alkaline to acidic. So the change in the pH converts one tautomeric form into another form, and also color will be changed. So here in the quinoid form, the structure will be changes. On means completely the structure won't change. Only in the structure a little bit will be changes. So based upon this change, we will get the different forms. So for example, if the starting solution is acidic in medium, means it may convert it to the alkaline, means basic. Or if the starting solution is basic, means it may convert it into the acidic form. And also the color will be changes. So the quininoid theory is mainly based upon the structural change. So for example, if you take the phenolphthalein, so phenolphthalein is the indicator, right? So if you take the phenolphthalein, so this is the structure of the phenolphthalein. So it is in the form of benzenoid form. See here, this is the benzenoid form, and it is the colorless when it is in the acidic medium. So colorless in the acidic medium. I said no that in the Oswald theory that when the phenolphthalein is dissolved in the acid means it does not give any color. So here all same has been occurred. See, when the phenolphthalein in the acidic medium means colorless, and when it is converted to the alkaline medium means basic medium, so it will get the pink color. So if you see the structures here, only little bit change will be formed, only little bit change. So let's see what is a little bit change. So if you see the structure here, here one of the bond is there between the, here carbon atom is there. So here if you see here carbon atom and oxygen atom, so between the carbon and oxygen one of the bond is there, and also here OH is there. But if you see here, the bond will be has been broken between the carbon and the oxygen. So here double bond is formed, and here one of the hydrogen atom is has been eliminated. So in place of the hydrogen, the double bond is formed. See here, this is the structure of the phenolphthalein. In the acidic medium, it gives the colorless. See, if you see the structure here, there will be the bond between the carbon and the oxygen. Carbon and the oxygen, one bond is there. And here one of the OH is there. So if you see in the alkaline medium, here one of the bond has been broken, and this bond has been converted to the double bond here. And also here one of the hydrogen has been eliminated, and here double bond is formed. And also the pink, the solution has been changed to the pink color. So Oswald theory is mainly based upon the color change of the indicator. Next, quininoid means it is mainly based upon the structural change. So that is this is about the Oswald theory and quininoid theory. So these are the references book should be followed for this topic. Thank you.